Well, welcome to this explainer. Today, we're actually putting on our detective hats. But instead of dusting for fingerprints or interrogating witnesses in a dark room, we're going to use mathematics to uncover the objective truth. We are diving into the incredibly fascinating world of hypothesis testing with normal distributions. This is the exact real-world statistical system that scientists, engineers, and regulators use every single day to investigate claims and separate fact from fiction. Okay, let's dive into this. Here's the roadmap for our investigation today. First, claims and statistical evidence. 2. The distribution of means. 3. Case 1, the juice carton. 4. Case 2, the machine bolts. 5. Critical regions explained. And finally, 6. The hypothesis testing toolkit.
Section 1. Claims and statistical evidence.
So every great investigation starts with a bold claim, right? Whether it's a manufacturer stating their new battery lasts exactly 50 hours, or a company guaranteeing a specific volume of soda in their cans, these claims really form the baseline of our reality. But as statistical detectives, we don't just take their word for it. No way. The question is, how do we actually prove a company's claim is false, or at least highly improbable, using just a small sample of data? I mean, we can't test every single product a factory makes. That would literally destroy all their inventory. Instead, we rely on a beautifully objective system called hypothesis testing.
To pull this off, we basically set up two competing theories. First up is the null hypothesis, or H0. Think of this as our innocent until proven guilty baseline. It represents the population mean exactly as the company claims it to be. On the flip side is the alternative hypothesis, or H1. This is what our investigation suspects might actually be happening out there in the real world. Perhaps the true mean is strictly less than, strictly greater than, or simply just different from that baseline claim. Section 2. The distribution of means. Now, before we can officially open our first case file, we need to quickly grab the mathematical magnifying glass we'll be using to examine our evidence. This is known as the distribution of sample means. If you take a random sample of size n from a normally distributed population, the mean of that sample, which we call x bar, is also normally distributed. But here is the absolute secret sauce. We don't just use the original variance. We divide the population variance, sigma squared, by our sample size n. Why? Well, because the larger your sample, the tighter and more reliable your average becomes. The extreme highs and extreme lows basically cancel each other out, making the distribution of the means way narrower than the distribution of the individual items. Section 3. Case 1. The juice carton. Armed with that mathematical logic, let's crack open our very first case file. It's a classic scenario of consumer protection. Here are the facts of the case. A company sells fruit juice, and they're claiming the mean amount per carton is 60 milliliters, with a standard deviation of 3 milliliters. But a local trading inspector starts receiving complaints that the company is shortchanging people. So what does the inspector do? They pull a random sample of 16 cartons and find an average of only 59.1 milliliters. The company says 60, the sample says 59.1. Is this just a run of bad luck, or is the company actually lying? We're going to test this at a 5% level of significance. Now, what's really interesting about this slide is that shaded area right there on the left of the bell curve. Because the inspector only cares if the volume is less than 60, they aren't complaining about extra juice, right? This is what we call a one-tailed test. We calculate the probability of getting a sample mean of 59.1 or lower, assuming that 60 milliliter claim is completely true. The math gives us a probability of 0.1151, or about 11.5%. And since 11.5% is greater than our strict 5% significance threshold, it's just not rare enough. There is simply insufficient evidence to reject the null hypothesis here. The company gets to keep their 60 milliliter claim. Section 4, Case 2, the machine bolts. So our trading inspector might not have cracked the juice case, but our next file requires a slightly different statistical technique altogether. Our juice case used a one-tailed test because, remember, we only cared if the volume was too low. But sometimes we care if a process is just off in either direction. If we're looking for a change in one specific direction, like less than or greater than, we stick with a one-tailed test. But if we're checking for an alteration in either direction, meaning the new mean just flat out doesn't equal the old mean, we absolutely must use a two-tailed test. Let's look at the facts for case 2. We have a machine producing bolts with a claimed mean diameter of 0.580 centimeters. The machine goes in for servicing, and we need to know if the calibration got messed up during the process. We grab a sample of 50 bolts and find a new mean of 0.587 centimeters. Our alternative hypothesis here is simply that the mean does not equal 0.580 anymore. It could be bigger, it could be smaller. We are testing this at a very strict 1% level of significance.
And this brilliantly illustrates how a two-tailed test completely changes the game. Because we're looking for an error in either direction, that strict 1% significance level gets split right down the middle. We place 0.5% or 0.005 in the extreme left tail and another 0.5% in the extreme right tail. These shaded sections are our critical regions. If our sample falls into either of these extreme zones, well, the machine's calibration is officially broken.
Section 5, Critical Regions Explained.
Okay, so you might be wondering, how do we find the exact numerical cutoffs for these mathematical boundaries without doing complicated calculus every single time? Easy. We standardize our test statistic. We use a nifty little coding formula to translate our specific, messy, real-world numbers into a universal standard normal variable, which we call Z. It's a three-step process. Step 1, we take our sample mean and subtract the assumed population mean. Step 2, we divide that by our adjusted standard deviation, which, remember, is sigma divided by the square root of our sample size n. Step 3, we compare this shiny new standardized Z value against a universal percentage points table. It's basically a mathematical translation matrix.
When we run those numbers for the machine bolts in reverse to find the actual physical diameter limits, we find that the upper critical boundary is exactly 0.585 centimeters. So the crucial point is this. Our post-service sample measured at 0.587 centimeters, and 0.587 is definitely greater than 0.585. It falls squarely inside that shaded critical region. The verdict? We reject the null hypothesis. There is sufficient evidence at the 1% level that the mean diameter of the bolts has indeed changed. The mechanic definitely needs to be called back to fix that machine.
Section 6, the hypothesis testing toolkit.
We've successfully navigated both a one-tailed and a two-tailed investigation today. To consolidate everything we've just learned, here are your absolute rules of engagement. The standard normal distribution has a mean of 0 and a standard deviation of 1. When taking a random sample of size n from a normally distributed population, the sample mean is normally distributed with its variance divided by n. And finally, you can universally standardize literally any sample mean using the Z formula to find your exact critical regions. Make sure you remember these, because this is your master key for testing statistical significance.
Hypothesis testing is incredible. It empowers us to hold companies, systems, and claims completely accountable to mathematical reality. But, it also leaves us with a really fascinating philosophical question. If statistics literally shape the standards of our modern world, how certain do we truly need to be before we reject a claim? Is a 5% chance of being wrong acceptable to you? Or do we demand 1%? The math gives us the tools for sure, but setting that ultimate threshold of truth, well, that's completely up to us. Keep questioning the data, keep testing those hypotheses, and thank you so much for joining me on this explainer.